Dispersion losses in optical link is the topic of this lecture. We have seen in previous lectures that the losses are there in optical link communication. There are different types of losses. When the signal travels in the form of light, the signal quality is degraded. The degradation in the signal quality is due to a number of factors, and accordingly, depending on different factors, the losses are classified. So in previous lecture, we have discussed about propagation losses in the optical link. This lecture is especially about dispersion losses, because the dispersion loss or the dispersion phenomenon is an important phenomenon in the optical link. So when we discuss about the losses in fibers, especially dispersion loss, we need to understand what are the main factors, what are different reasons of the losses in optics. If you can see this picture, an interesting picture, which says everything about what are the reasons for the losses. The very first factor which is written here, impurity. If there is any impurity inside the material, it causes absorption, scattering, any impurity, manufacturing, defect in composition of materials while manufacturing the fiber, bending, splicing, heterogeneous structures, inhomogeneity, are the different factors. And we know that in previous lectures we have seen that based on what factor is responsible, we call the losses as intrinsic or extrinsic. So various losses in optical fiber are due to either intrinsic or extrinsic factors. Fiber attenuation, which is also called signal loss or fiber loss, is consequence of intrinsic properties of optical fiber. Intrinsic properties that may include impurities, manufacturing defect, and other properties of the materials. It's found both in multimodal and single modal, or single mode and multimode fiber. There are some other types of losses which are related to link loss, bending loss. There are other factors which also cause some losses, which is attributed to extrinsic losses. But since the focus of this lecture is on dispersion losses, so we will focus on dispersion losses only. But before we discuss dispersion losses, we will see what different types of fiber are there, that is fiber types, how they are different, because when we discuss different types of dispersions, we'll find that the dispersion losses are different in different types of fibers. So therefore, we need also to understand what types of fibers are there. Fibers are actually divided on the basis of grading. We know when there is a core and then cladding, we know that there is a core material, it has certain refractive index, After core, there comes cladding, which has another refractive index, which has a material having some refractive index. So at the core cladding interface, there will be relation between refractive indices. There will be refractive index profile of both the regions. And how does that grading? Grading means how does it change? That grading profile means it's not pure material, it has been constructed as a specific material, although core is always supposed to be of pure silica or pure glass material. So, uh, accordingly, there are two types of fibers. You can see here step index and graded index. And the names are very simple. You see that the refractive index profile, N1 is the refractive index of your core area and N2 is the refractive index of cladding area. A is the radius of core and B is the radius of cladding. You see in both the figures, both the diagrams. So if the change, because we know that when we go from core to cladding or cladding to core, we we move, then we find that there is a change in refractive index. How is the change? If the change is like this abrupt change you see here at the core cladding interface, if the change is is abrupt, sudden change, just like a staircase where you just step up or step down and there is abrupt change at the level. So it's looking like a step, therefore we call it as step index fiber. Whereas in the second one, why it's called as graded index because of, you see the variation is not abrupt, not sudden. Slowly it's varying and then it's reaching to the next level. So step index, graded index means based on refractive index profile. How does refractive index profile change when we go from core to cladding? Accordingly, we call these fibers as step index and graded index. So, and there is another category, single mode and multi mode. We know that the light travels in the form of, the pattern electromagnetic field, which has different modes. It is also considered as, the propagation of electric field, which has certain number of modes. So, multi-mode and single mode fibers are also the types of fiber, characterized by the way light travels down the fiber and depend on both wavelength of light and mechanical geometry of the fiber. The classification is based on geometry as well as the wavelength, and the way light travels, there are classifications. Here we can see that single mode means there is only one pattern which is transmitting from one end to next end, one end to other. Whereas in the second and third diagram, you can see that it's multi-mode. Why multi-mode? There are different types of patterns. There are different field patterns. There are different modes of field which are traveling from one end to other end. So it doesn't have single mode. Rather, in both the cases, there are more number of modes. Multiple modes are there. But in the multiple mode case also, there are two cases. One, graded index, and second is the step index. When there is step index, then the patterns and the movement looks like this. And when it is a graded index, you see that, straight line slope like structures are there when it's a graded index, a step index. In a graded index, variation is not like this, what we can see in the step index. So these are the variations or changes between graded index and step index. That too, both are multi-mode. What is another interesting thing, since in multi-mode graded index, all there are different modes, but ultimately they are combining somewhere and we are getting one beam. But here there is a scattering kind of thing, and in multimode step index fiber, we are not getting a final single beam. Rather, there are multiple beams which we can see in the output. So single mode fiber is fundamental zero order mode is transmitted in the single mode. There is no first order, second order mode, third order mode, because there is only one mode. So we can say zero order mode is transmitted in single mode fiber. The light beam travels straight through the fiber and no reflections from one core cladding interface. You see here, straight forward it moves. There is no bending or there is no reflections anywhere in the core cladding interface. The single mode fiber is characterized by the wavelength, cutoff value of wavelength, which further depends on core diameter, numerical aperture, and wavelength of the operation. It really depends on the cutoff value of wavelength, and which depends on that further depends on core diameter, numerical aperture, and wavelength of operation. The single mode fiber propagates only the fundamental mode, that is one mode, and therefore there is no modal dispersion. When there are no multiple modes, so there is no possibility of having any interference or dispersion. So intermodal dispersion is not there in the single mode. The bandwidth required is much large with a single mode fiber than that of a multi-mode fiber, which means that pulses can be transmitted much closer together in time. I hope this is simple. When bandwidth is large, so bandwidth is defined in terms of frequency, so the time slot will be less, and therefore the pulses can be transmitted much closer together in the time because bandwidth is very high. Used in modern long range communication system. The single mode fibers are used in long range communication system. The typically core diameters which are there in the single mode are 5 and 10 micrometer is generally the range of core diameter, 5 micrometer to 10 micrometer. Okay, the actual number of modes, how many modes which are propagated through a fiber depends on how many modes are there, how many such patterns are there. That depends on core diameter, the numerical aperture, and wavelength of light. The normalized frequency parameter, sometimes we call it as a V parameter also, or V number also, is calculated by 2 pi a divided by lambda, where we have seen a is the core radius, L is the lambda is the wavelength, n is the index of core and cladding interface, that is n core and n cladding. So you can see this number, this normalized frequency parameter, it depends on core radius, numerical aperture, and wavelength. So therefore, core diameter, numerical aperture, and wavelength are the factors on which the actual number of modes, which is decided by V number. V number actually decides how many modes will be there. So that depends on core diameter, numerical aperture, and wavelength. The condition for single mode means when there is a single mode, so your V number must be less than some cutoff value. And cutoff value is 2.4. 2.4 is the cutoff value. And V number is supposed to be less than that for single mode operation. Otherwise, it will be multi-mode. Cutoff wavelength is below which the fiber will propagate, will allow propagation of multiple modes, and expressed as this one. Lambda is greater than lambda cutoff, which is 2.6. You can see 2.6 A into NA. This is not in terms of V number, this is in terms of lambda wavelength. If wavelength is greater than cutoff wavelength, which is 2.6 A into numerical aperture, then the propagation will be multiple. See, what we are discussing is whether multi modes, whether there will be multiple modes or single mode. They are mainly depending on V number, that is core diameter, wavelength. So in the first discussion we have seen that is V number, which further depends on numerical aperture and wavelength. So based on V number, there is cutoff value. If the cutoff value, if the V value, V number is less than cutoff value, it's single mode, otherwise multiple mode. In terms of wavelength, if wavelength is greater than the cutoff wavelength, the cutoff wavelength is below which the fiber will allow propagation multiple modes. Otherwise, there will be single mode propagation. Next one is multi-mode graded index. Multi-mode graded index. Multi-mode has again of two types: multi-mode multi-mode step index and multi-mode graded index. So multi-mode graded index, you can see the core diameter is much larger than the single mode diameter, single mode fiber. So the first difference is core diameter is larger than that of single mode fiber. Higher order modes are propagated, that is of order 1, order 2, order 3. The core in graded index fiber has an index of refraction that radially decreases continuously from center to cladding interface. We have discussed this when we move from core to cladding. So the refractive index does not change suddenly, but the change is gradual. Therefore, we call it as graded index. And this is the reason why the light travels faster at the edge of the core than in the center. Because when you reach there, the change is much there, and that's the reason. The different modes travel in curved paths. We have seen in the previous diagram with nearly equal travel times, which reduces modal dispersion in the fiber. Because in the graded index multi-mode, all the curved paths which we have seen, that mostly travel in the same time, and therefore the possibility of, you can see this one, the possibility of the modal dispersion is not there. The different modes travel in the curve path having same time duration will reach almost at the same time. The bandwidths are significantly greater than step index fibers, much lower than that of single mode fibers. The step index, in case of step index, bandwidth is larger, but the bandwidth is lower in case of as compared to single mode. When we compare multi-mode, there are two: graded index and step index. Graded index has more bandwidth and step index has less bandwidth. Typically, core diameters for graded index fibers which are considered are 50, 62.5 and 100 micrometer are the typical values of core diameters which are chosen. The main applications of the multimode graded index fiber is in medium range communication, such as local area network. When we connect fiber optic in local area network, this type of fiber is is used. That is multimode graded index fiber. Then comes multimode step index fiber. There are different modes in step index fiber that travel that travel different path lengths in their journey through fiber. The data transfer distances must be kept small to avoid considerable modal dispersion problem, because they are not, all the paths do not travel in the same time, so there is a possibility of the dispersion. So in order to avoid dispersion, the data transmission must be used for small distances. Step index fibers are available with core diameters of 100 to 1500 micrometer. Okay, so you can see that the core diameter is much larger. These are all well suited for applications requiring high power densities, such as medical and industrial laser power delivery. In these type of applications, multimode step index fiber is used. This is one comparison of all different fibers. You can see that single mode fiber has bandwidth 100 gigahertz. It's a bandwidth distance product. Graded index at 1300 nanometer, 500 megahertz, 160 megahertz at 850 nanometer wavelength. And the step index has very limited bandwidth. But single mode has higher bandwidth than the step index. The bandwidth measures the data carrying capacity and also expressed as a product of data frequency and the distance traveled. Therefore, sometimes you can see that the distance is always multiplied. Say 400 megahertz kilometer, it means that 400 megahertz for a distance of 1 kilometer. So when we say 100 gigahertz kilometer means 100 gigahertz frequency for 1 kilometer distance. Or we can also say 400 megahertz per 1 kilometer or 20 megahertz per 20 kilometers. So if you multiply, it becomes 400 megahertz 1 kilometer. So that's basically a product of distance and bandwidth. The primary limit on bandwidth is pulse broadening. The main problem which happens is pulse broadening that results from modal and chromatic dispersion of the fiber. Pulse broadening, the pulse duration broadening. The pulses which are, because we know that the light travels in the form of pulses. So pulse broadening is a problem. So let's see what is dispersion loss. This is a measure of temporal propagation that occurs when a light pulse propagates through an optical fiber, sometimes referred as delay distortion because delay of diffusion time makes the pulse wider. As I told you, pulse widening, there is a delay, so pulse gets widened. The propagation delay. This is spreading out of light pulse in a time as it propagates down the fiber. Spreading up the light pulses when it propagates down the fiber from one end to other end. It includes modal dispersion, material dispersion, waveguide dispersion. The dispersion losses are mainly of three types: modal, material, and waveguide dispersion. As the optical pulses travel the length of the fiber, the pulses are broadened or lengthened in time, called as dispersion. So what's dispersion actually? Dispersion is defined as pulse broadening or pulse lengthening, where the pulses, the light pulses get broadened. This sets upper limit of data carrying capacity of the fiber. If there is so much of broadening, it will put the limit on bandwidth of using the optics or fiber. Chromatic dispersion is the different wavelengths because the name chromatic. So chromatic is related with wavelength. So different wavelengths travel at different velocities. We know that down the fiber. The light sources provide power over a range of wavelengths and the pulses spread out along the length of fiber as they proceed. In this case also, the pulses are broadened. That is due to dispersion problem. Chromatic dispersion. Modal dispersion, different fibers reflect at different angles which they proceed down the fiber. Each modal angle produces different path angle for the beam. When they move at different angles, they will have different paths. Higher order modes reach out output end of the fiber behind the lower order modes. The lower order modes will reach first, then higher order modes. Next one is waveguide dispersion. This is due to the geometry of the fiber and it is because of different propagation velocities for each of the mode. And this is why all the modes will have different propagation velocities and that causes dispersion of the pulses called as waveguide dispersion. So all these can be seen in this picture that modal dispersion, you see there is an interference between the two modes. Material dispersion is due to the some decomposition, some composition factors inside the material itself, and waveguide dispersion where you can say there are different wavelength and different colors having different velocities are traveling. But what is important is In the dispersion, you see there is an input pulse, and when you compare input pulse with output, you will find that it has been broadened. So there is a broadening of pulse whenever we talk about the dispersion losses. Modal dispersion, multimode fibers can guide many different light modes due to large core diameter. Each mode enters the fiber at different angle and travels at different paths in the fiber. Since each mode travels a different distance, it propagates the ray arrive at different times at the fiber output. Light pulse spreads out in time, which can cause signal overlapping. This may cause signal overlapping. And the dispersion is not a big problem in single mode fiber because there will be a single mode. So the possibility is not very high of the dispersion in the single mode fiber. This is about the modal dispersion. So the next one is material dispersion. This is you can see here that chromatic dispersion is one of the phenomenon because of that pulse broadening happens. If you compare the transmitted pulse with the received pulse, the pulse is broadened. So this is a result of fine line width of the light source and dependence on refractive index of the material of the wavelength. There is a type of material dispersion called as chromatic dispersion, and the pulse spreading takes place and the velocity of light through fiber that also depends on the wavelength. So the pulse broadening is taking place. This is the plot between the refractive index and the wavelength. If you can see in the fused silica, when we increase the wavelength value, the refractive index is decreasing. So there is the relationship between refractive index and the wavelength. So when we say that something is depending on wavelength, and then obviously it will depend on refractive index as well. The next is waveguide propagation. The waveguide dispersion, I'm sorry. Waveguide dispersion, this occurs in single mode fibers. Some light travels in the fiber cladding compared to most light travels in the fiber core. Some light travels in the cladding area. When there is some light, some part of light traveling in the cladding area, it means there is a loss. Otherwise, the whole component of light is supposed to travel in the core area. But when it is not happening, it is also traveling to some extent in the cladding area, then it is your loss of signal. Since fiber cladding has lower refractive index, we know that as compared to core, the light ray that travels in the cladding travels that is faster than that in the core. That is an interesting thing. The refractive index is low, so the wavelength will be more. So wavelength is more, means the velocity will be very fast, and this is why the light rays travel faster in the cladding area. This is also a type of, I have already told you, chromatic dispersion, which is that depends on core size, V number, wavelength, and light source line width. Light in cladding moves faster than light in core. I have told you. This has been shown in this particular diagram. Power transmission has to be slightly discussed in this lecture. The amount of power that a fiber can transmit without any loss is expressed in terms of maximum acceptable power density. That's what I can say, an indicator of how the transmission is, how well the transmission is. The power density is a product of maximum power output of laser and the area of laser beam. The power density. For example, 15-watt laser beam focused to 150 micrometer diameter spot that produces a density of, that's a power per unit area, we can say, power per unit area. So P by A, that is equal to 85 kilowatt per centimeter square. So you can understand effectively per centimeter square area of that laser, per centimeter square area of the material, the total effective power is 85 kilowatt. The output of pulse laser is converted to power per pulse also we can get it, and say per pulse laser that produces 50 millijoule in 10 nanosecond, that provides an output power of 5 milliwatt. So this is how we can compute. I'm sorry. The power density is calculated from spot size. What is the spot size? Accordingly, spot size affects the power density. To transmit the absolute maximum energy levels down the fiber faces must be absolutely smooth and polished and be perpendicular to the fiber axis and the light wave. That is one, means by which we can reduce the amount of loss due to dispersion. The beam diameter also need not be greater than approximately 1/2 of the area of the core or the diameter of the core. Otherwise, there will be more problem. If the beam is not appropriately focused, some of the energy may spill into the cladding that quickly can damage the polymer clad silica fiber. So whenever some signal goes towards the clad area, that's obviously one I'm sorry, loss, one kind of loss. So therefore, it's better to always use silica clad silica fibers, especially in the applications where high power density is the requirement. And this is how we have discussed about the dispersion losses. So let us summarize that losses are there in optical link communication system. There are different factors which are involved: impurities, bending, inhomogeneity, or then you are connecting two fibers are the main factors for losses. But in this lecture, we have focused on dispersion losses, and that is mainly of three types: modal dispersion, wavelength dispersion, and chromatic dispersion. In all the dispersions, whether it is wavelength, modal, or wavelength dispersion, something which happens in the dispersion as a dispersion loss, that the pulse is broadened. We have studied the effect of pulse broadening in different types of fibers as well, that in graded index and step index, how does it change? How does it vary? That factor also we have covered in this lecture. So that's all for this today. Thank you.